All right. So with that, let me share my screen here. Make it bigger. How's that size for everyone?
That's about, yeah, that's, I think it's in the reasonable range, but definitely let us know if it's too small for you, and I'll relay that information.
And yeah, it's been a minute. So why don't we take a little bit of time and just kind of reacquaint ourselves with where we are and what we've done, or maybe acquaint ourselves if some of us did not watch the previous one or dump that information from our brains over the holidays, and then we will push forward here. I think I'm following you. Let me follow you.
One last bit of just
yeah.
Yeah, it's, if people want to chat, we obviously disable the Zoom chat just because we have another chat, which is Discord, and forgot to mention that in case there's some new people. So just join us on the Ziverge Academy ZIO Meetups channel, which I will write the link here at the top of this page. So Discord,
nice.
3H, capital J, 9, capital M-E. Hopefully you have enough time to copy that.
Before we navigate away from here.
Keep posting it. I'll copy it around and move it so you'll have time if you wish to join.
Lovely. So what we do with a lot of these is we create a little to-do list for ourselves, and then we kind of work through it over a couple of sessions. And fortunately, it looks like past Kid and Adam, we're like looking out for current Kid and Adam and put together a relatively nice version of that. So if we look at what we have here, we said we wanted to implement this idea of this like actor-based runtime. So we'll go through in a second. We'll remind ourselves of what that is. We wanted to implement the ability to fork different workflows and have them run concurrently with each other and then join them. So it looks like we've done that. We can take a look at that for a second. And then we wanted to introduce a typed error channel. When we first did this, we just had this A. And so this was a workflow that if you ran it would eventually, if it terminated at all, it would just give you this A. And we wanted to model the possibility of failure. So we added in the E type. And it looks like we got a couple of to-dos for ourselves here. One is we wanted to generalize this E to include this concept of a cause of failure that can include the possibility of defects or interruption. So I think that may be probably we'll hit these in order, we'll see. But that may be a good opportunity to talk about a little bit of error handling and typed errors versus untyped errors. I think that's another thing that people kind of have questions about sometimes. So could be a good chance to hit on that. And then I think this is going to give us a little bit of the groundwork for supporting interruption, which is another defining feature of these systems like ZIO, is that you can interrupt these fibers or these running workflows when they're in process, which is really something you get with ZIO that you don't get with like Future. Once a Future's going, it's just kind of going, and there's not a sane way to interrupt it or say that it's not needed, which is a real issue for resource safety, because you can kind of start a bunch of things if like the user opens a web page and then they like close the web page and navigate away, and you're still like doing all this work that you don't need to be doing. And then I think we have our stretch goal here of implementing this concept of interruptible and uninterruptible regions. So this is probably something that you work with a little bit less directly if you're a ZIO user, unless you're doing something pretty advanced, but is kind of used to implement some of the ZIO operators. And the idea is that once you allow interruption, then to have things like resource safety, you need to have this additional concept of you need to be able to create regions where you say, I don't want to be interrupted here, because you might be opening a resource and adding a finalizer, and you need to make sure that you don't get interrupted between acquiring the resource and adding the finalizer. And then once you do that, you want to have even more advanced abilities to like really have fine-grained control of it, and say, well, I want this whole area to be uninterruptible, but then I want this little area here to be interruptible. And so we have this concept of regions that maybe we'll get to today, but I think like a final thing would be to implement that and kind of use some of that.
And it is very similar to scopes, right? I mean, as we've talked about a bit in the past, in terms of these sort of nested contextual zones, regions, scopes, whatever you name it. Maybe it's
Yeah, and in fact, it's also really similar to just how defining variables works. So I could do something like val x equals 1, and then I could open up a block here and say val x equals 2, and then open up another, sorry, I control Z you, don't need to do that, and have another block here and say val x equals 3. And within each of these blocks, this inner value is, I mean, here I'm just explicitly using shadowing, but this inner value is going to be the one that is x. So outside of all this, x is 1. Within this block here, x is 2. Within this inner block here, it's 3. Or if I wanted to, I could make it 1 again to kind of illustrate this idea that I can kind of do and undo things. I think we've got, we'll come back to these errors in a second here. Maybe let me just comment this out for a second so we can get this to run. So, let's run this thing here. So yeah, so here you can see it prints out, it's 1 within this block. And maybe if we wanted to, we could call this like inner, and those ones inner, and that one outer, and this one middle. Oops.
cool. And just perfect.
And so we see in the outer scope, this is 1. Then we get to override it within this middle one, and it's 2. And then in this innermost one, it's 1 again. And so you can imagine the same thing applies to like interruptibility of it's interruptible. And then in this region, we want to make it uninterruptible. But then in this part here of the uninterruptible region, we want to make it interruptible again. So that's this idea of regions.
And this is known as kind of lexical scoping, this particular like variable shadowing thing, which is that like lexically meaning literally like the lexical code that you have typed in. So the sort of visual, there's a visual sort of representation of the scope of this. You can sort of see the actual code that you wrote, and that represents something about the structure of the program. So yeah, it's nice. It's nice too. I think that's something that I really appreciate that, you know, Adam does with his teaching, and just sort of ZIO tries to embrace, is just sort of finding these patterns. That's the nice thing about functional programming in general, right? It's just our brains are limited. It's nice to be able to abstract different ideas and basically view them all as the same thing. You know, save some mental space. Run some compression algorithm on ideas and pack everything into the same idea. So lexical scoping, scopes, interruptible regions are really just the same idea. And it just ends up being this way that of us to think easily, right? We like to think in these kind of, it's how we write our code, these nested zones. And it's nice to have the behavior sort of apply to all child behaviors unless we override it for a subregion. I think it just, for whatever reason, is easier to think about. So that's probably why it shows up in lots of places as a desirable property. So anyway, we'll get to that later on, hopefully, maybe. Or session 4.
Yeah, exactly. Depending on how much review we do. Okay, so let's, I think I'm kind of slightly more than I should have. Let me uncover this again. So let's start with just kind of reviewing what we've done so far. So the first thing we did was we defined the ZIO data type, and we used this pattern of this ZIO itself is like this workflow. So it's like a description of something that you can run, and you can run it multiple times if you want to. So in a way, it's like a little bit like a Spark job, that like the execution plan itself is something that you could like submit multiple times, and each time it would run. And this ZIO itself is like this mini language that actually just has a couple of cases to it. So if we go down here, right now, our little ZIO language actually only has 5 terms to it. And so it basically says, well, you can just take any value you have, and you can create a workflow that's just going to return that value. You can compose these workflows sequentially. So you can say, run this workflow, and then use its result and run this other workflow. You can take some asynchronous callback-based code and you can import that into a workflow. You can create a workflow that just fails with a value. And we introduced this error handling one that lets you run. This is kind of like this flat map one, but it's just a little bit more powerful because it can handle errors as well. That says run this workflow, and then if it fails, run this, and if it succeeds, run this. And so this, in a way, was like really easy because like all we're doing is we're defining case classes here. And but having these case classes, we could actually quote unquote implement with kind of air quotes on it a bunch of different operators here. So like we could say, well, what it means, some of these are kind of obvious, so it's just the same thing of what it means to flat map is just return this flat map constructor. What it means to succeed with a value is just call that succeed constructor. But then what we did a little bit was we were just pushing back the actual work of like, okay, we've got this mini language, how are we going to execute one of these things? If we've got one that is a succeed and then a flat map and then a succeed and then another flat map, how, like, what does it actually mean to take that and to kind of run that program? And to do that, we implemented this unsafe run method. And what this does is it creates a fiber that's going to actually run this workflow. And so we created an interface for a fiber, which right now just has this one method that lets us wait for its results. So you can think of the fiber as like the in-process workflow. The ZIO itself is like that execution plan. So you could run it multiple times, but then it wouldn't make sense to say, well, I want to wait for its result because it's just a plan. Whereas the fiber is like, okay, there's some Spark job that's actually running on some set of machines, and you could wait for it to be done and could say you don't want it anymore, or maybe you could ask which machine it's running on. And that's the kind of the concept of a fiber here.
Yeah, and if you know what a future is, and if you've heard maybe us compare future to ZIO, where a ZIO is just this blueprint and a future is a running actual computation somewhere that started sometime in the past and might complete sometime in the future, a fiber runtime is essentially the ZIO's version of a future, right? It's a handle on an ongoing and executing ZIO computation. So yeah. Yep.
And then we've got a pretty traditional object-oriented pattern here. We have this interface. So this is just the interface of a fiber that says it's this running computation. It's going to either succeed with a value or fail an error. And right now, the only thing you can do with it is you can wait for its results. And then we've got this thing down here that's called fiber runtime that is our implementation of that fiber interface that's actually going to do all of this logic for us. And one of the key things we talked about in the first session was this idea that an actor can be a pretty good analogy for a fiber, because the idea of a fiber is that a fiber is a little bit like a thread in traditional like Java programming. It represents one logical flow of execution. And so just like with a thread, on a single thread, it's always one thing happens, another thing happens, something else happens after that. There's no interleaving of logic on a single thread. The way we have different things going at the same time is we have different threads doing those things. And so similarly, with the fiber is always only doing one thing at a time, and there's always only one execution of each fiber. And that helps us reason about things in a sane way, because when we're doing this stuff on the fiber, we always know we're doing one thing and then we're doing something else. There aren't kind of two things going on the same fiber at the same time. And in ZIO 1, so then if you have that idea of a fiber, a little bit of the challenge is like, how does the fiber interact with the external world? Because to get anything out of the fiber, it needs to communicate with the world in various ways. Right now we have this one way of, we want to say, hey, I'm interested in your result. When you're done, come back and tell me your result. Or we're going to want to implement this functionality to say, I don't want you to run anymore. interrupt yourself. I essentially want to kill you. Or maybe we have other things that are asking for information on the fiber of like, I want your status or something else. And so in ZIO1, a lot of that was implemented by just having different concurrent data structures that were in that fiber. So if you wanted to join that fiber, there would be like a set of observers that the fiber kept track of, and it would be a concurrent set because you would need to manage these concurrency issues of, well, what happens if the fiber is like done and at the same time someone else is saying, I'm interested in the result. Are they going to get the result? Or are they not going to get the result? And if you go back to our first ZIO from Scratch series, we had a bunch of stuff where we were kind of using these concurrent data structures, and we were using like atomic references, and we were showing how we had to like double check different things. And that, I think, was some of the like accidental complexity that was on top of the essential complexity. And so what ZIO2 does is it moves to more of this like actor-based model where actors are something that I think can be overused, right? I think a little bit of like the problem with ACCO was like every problem is solved with an actor, and like not every problem is like ideally designed for an actor. But this is actually a pretty good situation for a actor type interface, because the idea of an actor is it encapsulates this internal mutable state, and it says, well, the only way you can communicate with it is with these messages you send it, and the actor internally always processes the messages one at a time. So it gives you that guarantee, just like the fiber wants to have, that while you're processing these messages, you're only doing one thing at a time. And so what we did in our first session here is we implemented some of the logic for this actor type interface. And so we said that every fiber is going to have this thing called an inbox that is just a concurrent queue. So this is going to be like our one concurrent data structure that we're going to use here. And we're going to kind of in one place encapsulate all that tricky concurrency logic. And the way you communicate with the fiber is you call this offer to inbox message with one of these fiber messages. So you can think of, again, kind of going back to an actor, this is like the protocol of the messages that the fiber accepts. And what this is going to do is it's going to add it to the inbox. And then we have a little bit of extra tricky concurrency logic. There's like the one place we have to do it, where we say, if the fiber is already running, then once it checks the inbox the next time, it'll process the message and we don't have to do anything. If the fiber is not running right now, if it's in like a dormant state of it's waiting for like an asynchronous value to be given to it, then once we offer something in inbox, we need to kick off the execution so that someone actually executes that thing.
And that's to sort of handle these two race conditions where either maybe two different threads offer a message simultaneously, and then you execute the ZIO twice, which would be very strange when you only once, or one submits it the second something stopped running, and therefore no one executes that message. So you want to make sure that each message is processed, but only once. So yeah, that we sort of need to balance that with this atomic Boolean in this concurrent mutable queue. But that's the one place really, and everything inside of the running queue loop doesn't need to worry about dealing with concurrency, because we kind of handle it at the door. And then once we're in the house, we get to understand that we have this nice linear execution model. We can just use vars. We don't need to use concurrency primitives, and it's all a beautiful world. You know,
exactly. Yeah, and so we've got the rest of that inbox logic here. We've again got to do a little bit of double checking here of we're processing these messages that are in the inbox. And when we're done processing all these messages, we need to double check that we really don't have any new messages after we set our own running status to false, so that, again, we don't kind of have those race conditions if someone else offers us a message and they think we're running, but then we immediately stop running. So if you if you have more questions about that code, go back to the first video we did where we kind of go through the implementing this, and we go through the logic here in more detail. But so the payoff of this is that a lot of our logic outside of that gets to be very simple, where, like, let's look at this add observer method. So this is where someone is saying they're interested in the result of the fiber. And so all it is they sent us a message that was this add observer message. And if we go back to our, let's see, I think it's, that was a separate file, but I think it's just down here, trait fiber message. Right now, there are only 3 fiber messages we support. You can kind of say start initially, I'm interested in your result, or we use this actually to have the fiber kind of send us back an asynchronous value that we're waiting for. So if someone sends us this add observer message, all we do is we have this result, which keeps track of our final result. And so it's either going to be null if we don't have a final result yet, or if we're done, it will have that final result. And so all we do is we say, if we don't have a result, if we have a result, then we just give it to you immediately. Otherwise, we just add you to the set of people who are interested in our result. And if you look at this observers thing and this result thing, they're both just bars. So they're not any kind of concurrent set. We don't have to worry about any kind of race conditions. And that's because we have this guarantee that anytime anything is happening on this fiber, it's happening one at a time in a linear order. And so if the fiber is processing this add observer, it's not messing with the exit value because it's only in one place at any given time. And if it's changing the exit value, then it's not processing this observer right now. So it makes it really a lot more straightforward for us to implement code within the fiber, which is good because there's enough kind of complexity to some of the logic of the things we need to do that we don't need to add any more complexity.
Yeah, and if you go back to sort of the first time we did this in the first ZIO From Scratch series, all of this needed to have comparing sets, and basically the observers needed to be inside of an atomic reference. And we basically need to do that thing that we were sort of just doing in this one place in the drain queue on current executor, or rather the offer to inbox. And so far we've really only earned this one bit of state from it, this observer state. But as I'm guessing, add interruption, it's going to start compounding interest, right? We've paid the concurrency cost once at the boundary, and now as we add more and more state, we don't need to, every time we add a new variable or mutable entity inside of our loop here, we don't need to once again have more concurrency primitives and concurrency thinking, which needs to be very precise and is tough to get right. So yeah, cool. That it looks really nice in here.
Yeah. And so then beyond just this messaging processing logic, the core logic is in this method called run loop here. And this is just going to go through and one at a time execute each of these terms of that ZIO language that we saw before. So all we're going to do is when we kick off start, so this fiber gets defined with a ZIO value. So this is the ZIO that the fiber is running. And the first thing that we're going to do is we're going to set that current ZIO equal to the ZIO we have. And then we're going to do this run loop thing. And so we're just going to take each of these terms one at a time. And some of them are very simple. So if it's just succeeding with a value, then we're just going to return that value, and we're going to call each of those observers with that value. If it's saying, we'll do this thing first and then do this other thing, we're going to switch to doing the first thing. And that's why it's this loop here. And then we're going to push onto the stack this continuation of the next thing that we want to do. And so this explicit stack is the thing that makes ZIO stack sync. Of if we have these deeply nested things that say do this thing and then this thing and then this thing, and there are a million things, we're not going to stack overflow because we're going to push these things onto this stack that we are maintaining ourselves. And that's also going to let us do additional things with that stack. So for example, in that fail operator, if we fail, we're going to look at that stack and we're just going to kind of skip ahead in the stack until we get to something that is actually able to handle that failure. And that's why we created these continuation on success and continuation on success and failure types, so we can distinguish whether one of these continuations is actually able to handle a failure or not. And I think the one other one here that we spent some time on was this async one. And that's quite powerful because it lets us import callback-based APIs into ZIO. So one of the really nice things about ZIO is you don't have to manage callbacks yourself and kind of have the like Hadouken of like the callback, 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 callback. And it's actually pretty nice how that's implemented. When we get to one of these async things, we just stop running ourselves and we give the callback-based API a callback that says, hey, when you've got a result, send it to our inbox, and then we'll process it. And so this gave us a very simple way to describe these asynchronous computations. And that ended up being really important because this async is actually how we implement this join operator. So if we look at the implementation of join, all join does is it says, add an observer to this fiber and tell the fiber when it's done to call us back with its value. And so we were able to use that to implement the zipar operator that lets us run two things at the same time. And so this was kind of our proof. If we go back to our like checklist at the beginning, that we were able to do parallelism and concurrency here. And I think so I think we may have upgraded this to Scala 3. So I think we have minor compilation errors here, but let's fix those.
Oh, 3 now, fancy. All right.
Yeah. So I'm just going to give ourselves a little helper method.
Nice.
And so this is basically going to take a
nice.
and then I should be able to use this to fix these.
Cool. Everything is erased.
Okay. Yeah. All right. Let's try to run this. Okay. And we're getting some message right now that says yay and whoops, which I think comes from this one that we were doing with that error handling. But let me try doing this my parallel workflow one.
Yeah, yeah. Good to just double check that everything's still working.
Yeah, exactly.
All right.
So this one of these should take 3 seconds. One of them should take 5 seconds. And so we see, I think we had a little bit of startup time, but this finished in 6 seconds versus if these things weren't in parallel, this would have taken 8 seconds. So that's a nice validation that we've got parallelism working, which is pretty cool. I mean, this is not that many lines of code, especially excluding kind of our like scratch notes and stuff. So we looked at our active runtime. We just looked at forking. And then we talked a little bit about this error channel we introduced, that we introduced this idea that you could fail with this error of type E. And the key things that were kind of special about the error was we can introduce it with this fail operator. We can handle it with these operators like hold ZIO or catch all. And that errors had this short circuiting semantic that if we go to like this example here, so here we're going to run succeed, yay. We're going to print line that. Yeah, let me run this again. Let's look at this for a sec. So we see the yay prints. Then we failed with this whoops. And because we failed here, we're going to skip over all these continuations until we get to one that is an error handler. And then we're going to run that error handler. And that semantic is pretty important because we have a lot of cases where you can imagine we have some logic that says, we'll get this thing from the database and then do this analysis on it and then do this other analysis and then write it this other place. And if you can't get a thing from the database, there's no point in doing all of those other things. And so this like short circuiting just embodies that idea.
And I think maybe I'll just do one more little was like the ASCII simulation. The important thing to note, because it can be a little difficult at the beginning, like what does this represent? Well, we talked about how this turned into basically a series of case classes. We kind of looked at those case classes above, and it's basically built from the top down. So there's the catch-all node that contains a flat map that contains a flat map. So at the very core, you have to sort of dig all the way down before you get to that succeed node. And so when we're sort of in the run loop, sort of piecing this apart from the top down, working through this, sort of chiseling away at it towards its the core, we are getting all these continuations, and we have to store them somewhere. So we push them onto the stack. So we have that kind of, we put the cache all in the stack, and then we put this, done something else print, that flat map node. We put that on the stack, and we had two of those, and then we have this other flat map that will actually fail, and then we have this another flat map again, which is going to print success. And then finally, we have at the very inside, we have succeed. And when we get to a succeed node, then we can use that and start pulling these continuations off of our stack. So pulling it from the top. So we'll take our yay and put it into there, which is going to print, that message success yay, which we do. And of course, this gets us a result, which happens to be unit, because that's the result of print line. And we're going to take that unit and pass it into the next callback, which is going to take that unit and just fail with a message. So what we've done is we've actually printed success, and now we've failed. And because we've reached a fail node, when we process a fail node, we unwind the stack looking for a catch-all continuation. So we're going to just throw away every value off of the stack that we had until we come to a catch-all node. And then we're going to pass the error that we had, which was this whoops, into this continuation. And that's why we then end up as our second actual concrete step, printing error whoops. Not sure if that helps, but it's nice to sort of go step by step a little bit through this. But yeah, okay.
Yeah. All right. So that was maybe a relatively long recap. Does anyone have any questions before we push forward into new stuff here?
Nothing in the Discord yet.
Right.
Hopefully everyone who wanted to chat has made it to the Discord. And there are people
awesome.
Frustrated.
So we want to work up to implementing this interruption, because that's kind of this like cool feature of these things that would be really cool if we could do. But before we do that, we need a little bit more groundwork for ourselves. And the basic problem right now is, if you look at this ZIO, right now you could say the contract of this thing is, we could say the ZIO is a workflow that will either succeed with an A or fail with an E. And if we want to support interruption, there's this question of, okay, well, like, let's say that we interrupt this workflow while it's running. We interrupt the fiber that's doing it. What should the return value of that be? And I mean, clearly it's not an A, because we interrupted it before it produced the A, so it doesn't have an A. But also this E is this generic type, right? The E could be anything. It could be nothing. It could be some custom data type. It could be a string. It could be a throwable. So we don't have a generic way to produce an A. And so this representation here, we could say is not rich enough to describe this possibility of interruption. And as we get into this, we'll see it's also potentially not rich enough to describe some other things as well. And so what we're going to want to do is we're going to want to change our definition of this slightly. And we're going to say that instead of this, ZIO is a workflow that will either succeed with an A or fail with what we call a cause of E. And so a cause of E, right now we're going to just start with the simplest cases, is basically going to be two things. It's either going to be a fail that has an E inside it, or it's going to be an interrupt. And the interrupt might just say, you're interrupted, or it might have something like, in ZIO itself, there's this concept of a fiber ID. That's basically, if you were murdered, the fiber ID is like the person who stuck the knife in your back. So the cops can kind of know who was responsible for you being interrupted. So let's start working through how we would implement that. So I think the first thing I'm going to do here is I am going to find some space here, I think down here. So we already had this concept of an exit. And the exit just represents all the possible values that one of these ZIO workflows can terminate with. And so before, this perfectly reflected the original version of what we said, of the result of one of these workflows is either a success that's an A or a failure that's an E. And so to change this, we're just going to change this E to be a cause V. And we're going to create this cause data type. And it's already creating the constructors for this. And I think initially we just have these two constructors. So we could say one is fail. It's just going to have the E inside it. And so if all we've done, if that's all we do, then so far we basically have exactly the same thing, except we've kind of added more ceremony to it. We've kind of had one additional layer of wrapping. But we can actually have these additional cases. And so one of these is, maybe I'll make this a case object right now, is going to be this interrupt. And then it's also created this other one called die that doesn't relate so much to interruption, but relates to the idea that totally unexpected errors could happen. So even if I have a data type that's like ZIO nothing int, and maybe this is just like ZIO.succeed 2 plus 2, clearly adding 2 plus 2 should not fail in any way. If, well, this thing, well, so yeah, I could divide it by 0, or even if it's just I'm doing 2 plus 2, maybe while this 2 plus 2 is calculated, I'm like pouring some Diet Coke on my MacBook here, and like I'm getting some crazy like error from my machine. You always have this like possibility that kind of an unexpected error could happen, that like an earthquake could happen. For at least, yeah, I live in Los Angeles, so that's, I guess, my relevant version of calamity. But depending on where you are, you can pick the one that applies to you. And so this die exception would let us model those unexpected types of errors. Okay, so we've got this modeled in. Now we basically just need to push this through to everything else, and we're probably going to get some help from the compiler here, and we may have some blowing up or figuring things out ourselves, because at least within the runtime itself, we are more dynamically typed. But okay, let's kind of follow some of these through. So some of these are also going to reveal that we need some additional operators here. So let's actually create a couple of additional operators for ourselves. So the first thing I think we're going to do is this fail. We're now going to want to have a way to actually fail with these different richer causes we're creating. So we're going to change the signature of fail from failing with an E to failing with a cause of E.
Mm-hmm.
And then I'm going to implement a richer version of this cause constructor that I'll call fail cause. And this will just let me specify a cause. And yeah, now this can just be that. And then this one can just be fail cause, fail E. And maybe if we want to, we could implement a little helper method for us down here, cause, just so we can use it directly.
Nice.
Okay. So now we go back to our fail cause. So now we've got a way to introduce these richer types of errors. And I think there's a pattern you probably, if you go back to our previous video, you've seen before of we kind of start with an operator, and then we like generalize to like more powerful variants of it, and then we implement the simpler variants in terms of the more powerful one. Okay, and let's yeah, perfect. And then the other thing we're going to need is, so just like we needed a way to introduce errors and we need a way to recover from errors, we now need a way to introduce these more complex causes, which we have here. And we also need a way to handle those full causes of failure. And so the most powerful operator for that in ZIO itself is this operator that's called fold cause ZIO. And if you use ZIO, there's actually, most error handling operators have a cause variant of whatever operator it is. And it's essentially the same signature, except that instead of taking the E, it takes the cause. So this is going to be the same, other than this fact. And then it's doing exactly the right thing of essentially, we're going to make this the new primitive. And so if we go here, I mean, we could call this fold cause, or maybe we still call it fold. But we're gonna, oops, sorry, I'm stepping on you. So we're gonna change this to be able to handle the cause. And then up here, so then this will now work. And now this thing can be implemented in terms of our new, more powerful one. And so we're just gonna say, well, if we've got a error here,
yeah, and one of the really nice things about just using a powerful statically typed language like Scala is that you can incrementally add levels of abstraction and sort of keep your head on straight while doing so, and just follow the compilers and just change the types, and then it tends to just work. Because it would be definitely difficult to understand if you just come in from scratch with this huge hierarchy and layers of indirection. But by building it incrementally, you kind of get a grasp of it the whole way up.
Yeah, exactly. And so here we can say, well, we've got this cause. And so what we might want to do is we might want to match on it. And we could say, if it's a fail cause, then we're going to call this on failure. And if it's anything else, then we're just going to fail again with this. And if we wanted to, we could extract this into like its own little operator, but I think this is probably fine.
Oh, I think we need to wait. Fail cause. Why is it said fail cause?
Oh, it doesn't know. We need to explicit. It doesn't know these are causes of nothing. So yeah, cause dot interrupt. Because cause dot by t.
Yep. Oh, oops. Yeah, now cause dot interrupt. There we go. Okay, yay.
All right. So I think now we've got the basic building blocks. And now we just got to probably use them in a couple more places. And so we can see the first one is this one here. So this is when we're actually running this workflow, we have this var result that's supposed to contain the final result of our workflow when it's done. And then we're going to run it. And then when it's done, and so here we want to use our fold cause ZIO instead of our fold ZIO.
Yep.
And then down here, when we have this thing, so this is now a cause, and this should be an instance of causity. All right, so that's what we've got from the compiler. Let's try running something. This is where having test coverage would be good, but it seems like at least our existing functionality seems to be working, which is excellent.
Of course, tested interrupts or dies, but that's okay.
Right, exactly. That's I think a good next step for us. And so yeah, let's look at that. So let's create like a new example. So val cause example. And so one thing we could say here is we could do something like, let's say I do ZIO.die with say a new illegal argument exception.
Mhm.
And then let's say I do a catch all and I do ZIO.debug, or I don't even have that.
No, I was
But
going to make.
you're going to make one, which is excellent. And so our expectation here would be this is actually, well, right now this isn't a cause. It'll be a cause in a second. But first let's kind of, yeah. So right now our expectation, oh, and we need to, here, let me make another convenience method for us to just die with the, let's see. All right. So our expectation now is that this caught is never going to be printed. And the reason for that is that this is just a catch-all. It's not a catch-all cause. So it only is going to recover from those typed failures. And that's really valuable behavior in a lot of cases because there's not really a sane way to recover from errors that are totally unpredictable, right? Like what logic are you going to put in your code of like, if Diet Coke is spilled on the user's computer by the user, make sure to do this thing. So it lets you kind of separate out your logic of handling your expected errors and only handling those errors from any logic for like what you really want to do in any case at all. So let's try running this. And so we can see we didn't get any output here. Now let me change this to catch all cause. And if we've implemented this right, let's implement catch all cause. If we've implemented it at all. So again, I'm just going to create the cause variant of this thing. And so this can now just be called cause ZIO. Okay, so now let's try running this. Nice. And so now you can see we get this error message. We caught this cause.die with this illegal argument exception.
Great.
Okay. So now we
have two options at this moment. We could continue to interrupt, but I guess there's also that case that we kind of looked at before, right? Which is that Diet Coke error. But if we did something similar where we had inside of a succeed and we threw something like this.
Yeah, let's look at that.
It'll be like
so
easy.
I think right now this is going to fail horribly, but it will be relatively straightforward to fix that. So let's try running this. Oops, yeah. And let this fail horribly. Yeah, so we see we get this completely, I mean, it does get printed to the console, but it is not handled well at all. This is not exiting cleanly. This is not nice at all.
It did not run our code, like it was not caught in the world.
It was not, exactly. And so what we want to do here is basically we're missing a try catch block in the run loop. And so what we want to do is we want to say, try doing any of these things. And then if you fail, then just set the next one equal to that failure here. So let's
like wrap this whole thing literally.
Yeah, we can kind of either wrap it here or we can do it in some of these some of the inner ones, but yeah, I think this is fine.
And then basically we want to set our current ZIO equal to ZIO.die of that throwable, right?
Let's see if we can run that. Let's see. Okay, so we are. So we are catching it,
but you know what might have happened? Maybe we should print something out as well.
Let's make sure. Yeah.
Throwable in run loop. Yeah, I guess the danger of this is we could be causing another error, and we're catching that and just setting the current ZIO. So yes, something weird could be happening.
Let's see.
So we know what's happening in succeed, right? So we know we're doing it basically when we're calling line 277. Is it 277? Oh no, the stack's not empty. So we know it's going to be there. There could, maybe there's a problem where we're handling the, so we're setting the current ZIO, but then maybe we're failing again just by failing to handle it. Because we would then be processing the fail node. Let's see what the fail node says. Running fail with cause E. Because that's where we get that, that cause. Oops. And actually, let's see. It's a function, of course, so I gotta call that cause thing. All right, so let's see if we ever get there with our cause. Maybe something bad happens. So we get, we're running fail with that, but then it seems like we're never processing it. I'm wondering if the cast here, we're doing something weird or something, I don't know. So what would find next error handler?
Well, let's see.
Yeah, did we make it there? So we
have an on success and failure. Are we?
That would be that one. Oh, wait, am I debugging correctly? Yeah, I'm print lining, I think so. So yeah, let's just keep adding print lines. Did we, where are we next? Yeah, I think we want to go to our the run loop, the fail node.
Yeah. So
continuation should not be null. So we're going to set the current failure to be on. So yeah, print line about to call on failure, and then print line, let's see, called on failure, current ZIO is, let's see what that is. Huh. Yeah, we got a ZIO succeed. So this all is making sense. Maybe we're doing something. Maybe we're just not logging this correctly. Catch all cause debug. Debug is just, we're doing something odd. What is catch all? What's our definition of catch all cause? Is that correct? ZIO succeed of. Oh wait, do we need to call ZIO succeed? Oh no, we do.
Wait, hold on a sec.
Oh, we can just.
Yeah. Well, it should be, because it should be the handler that's running.
Yeah, and in fold cause ZIO, we're going to take the on failure. Yeah. Calling it. Huh. And then it should be calling that ZIO succeed, which is the print line, I would imagine. But something weird is happening. Let's see. Print line debug. Did I screw something up with debug? I don't think so. And it's definitely not calling debug. So that's the odd bit. Called on failure, current ZIO succeed, lambda. I wonder if somehow we have a doubly nested ZIO. Yeah, let's print out what ZIO succeed is for sure. Should we do it like succeed? What's that? Aha, it's unit.
All right, so why? Oh, are we? Oh, hold on. I think we're not suspending something. Okay. Oh yeah, that should be suspending it.
Let me see if debug is ever called. Print line calling debug. So that should be creating the ZIO succeed. I feel like we're getting a nested ZIO or something, or I don't know. Well, yeah, why would it be? Can we run it one more time? So we did call debug, about to call on failure. So we're getting that ZIO succeed back. Maybe are we doubly nesting this there? So in the error handler, about to call on failure, we did that. continuation on failure. We're calling that with the cause, which called it, and that got us a ZIO succeed back, which should be a huh. Maybe this debug is, yeah, does adding the type there help or no?
Yeah.
No. Yeah, we have a ZIO succeed of a lambda. Where could it have gotten doubly nested? Okay. And then can you extend out your terminal? Actually, I just want to make sure what's happening in what order here? Where first we're catching. It's just so we're let's see what makes sense. So first we caught a throwable in the run loop, which then it threw again with a die, having ZIO. And then we found an error handler. And then we called that error handler's on failure with our handler, which should call indeed the debug, which should just print, it should now succeeds, just printing out the cause, calling debug, and then called on failure. Yeah. And then debug. Wait, it does say debug now. It is being called.
Yes, I think
it's working.
Maybe we hadn't saved something.
Something weird happened. Something weird happened. Maybe, yeah. I don't know.
All right, let's try to comment things out. Is it being printed twice? Let's just bring this up a little bit and let's kind of verify.
I'll remove the or comment out all the print. Oh, you got them. Okay, great.
Yeah, let's try. Okay. Okay, no. So one of these things is indirectly causing it to be evaluated, I think. I think this one.
Oh, because now it's not showing it?
No, that one isn't.
It doesn't even.
We got something funny going on. Yeah.
What the? What have we done?
So what are we?
How did that?
We have, oh, this one. I think.
Oh, it's probably up there. Yeah. Because we're calling the A. Oh. Now, okay, so what's happening here? Why is A not being called though? That's very odd. I guess we're doing a
should be here or here, right? It should evaluate either way. So yeah, let me take these out. And let's just focus on this.
Okay.
So this does it twice.
And if we don't print that out, it does it 0 times.
Oh, I'm wondering, do we have
if there's a continuation, I guess there must be a continuation, and then we're setting the current ZIO equals to continuation on success, and for some reason that is never. What is our continuation here? Print line. What is the continuation? I wonder if it's in our sort of run sync implementation. Oops, sorry. There we go.
Well, this should evaluate it in either case here.
Well, in here, we're doing it inside of continuation on success, which might be putting that inside of another thunk, right? Does on success take a thunk? Oh, no, I see.
So let's extract that out. Where are we here?
Can we run it one more time real quick? I'm just
Sure. Then I got a little, yeah,
okay.
So why don't we do, no.
But how?
Yeah, well,
I think
no,
it might be doubly nested. I think what that is I think evaluated might be another ZIO succeed. Is that correct? Wait, why is it not even? Oh, wait, we need to save. Maybe it's odd. Or is it print? No. Why is it not showing up? What the?
Oh, hold on a sec, because this is throwing an exception.
Well, that's okay. That's the die one. Okay, so so maybe with this other case then. Eval equals a as instance of a print line. Okay, lots of logs. Sorry, all done now. Well, whoop-de-doo.
Anyway, maybe we should come back to this. We can fix this offline, and we can come back to this next time.
Yep. Really tricky. Maybe we should have gone slightly slower. It's easy to add. The one danger, I guess, I was talking about how it's nice to refactor things and they just work. The one danger with this run loop and why tests are very useful is just because we're doing so much casting, and we are kind of throwing away the safety of the compiler a little bit because we have to. Okay, yeah, I'll delete some stuff now. I'm sure it'll be obvious the second we stop recording.
I know, exactly. All right, well, do we could do some of the stuff on start to work on interruption, or when we're also more than an hour in, we could break here and pick that up next time.
Yeah, maybe let's break here and next time, because I think what we could do is we'll have figured out whatever the silly error, so we can immediately show what that is, and then we can pivot to interruption and then get interruption, and then that's a lot of stuff.
All right, sounds good. All right, any questions from folks before we break here?
I haven't seen anything in the Discord. Yes, sorry for debug help.
No, it's probably it happens to everyone.
Live coding for you.
All right,
we'll see you all offline.
All right, bye.